In the last material and energy balances video, I described how Raoult's law can describe equilibrium for single condensable species. In this video, I wanted to briefly touch on some deviations from equilibrium that the problem statement could give you as a process specification for systems that are not at equilibrium. So I also said on the weather report, for example, when you're thinking about the humidity outside, that the system outside is not at equilibrium. But you may have heard of a relative humidity in the weather report. This is what they're talking about. So while Raoult's law would say that P star is equal to partial pressure, the relative humidity is a way to quantify if the partial pressure is a little bit greater than, a little bit less than the vapor pressure. So the relative humidity summarized here in this equation 6.3-4 is how you could, instead of Raoult's law, you would use this equation to give you the relationship between partial pressure and vapor pressure. And there's several other process specifications here, so I won't go into these in much detail. I just want to point you to your textbook and sections, equation 6.3-4 to equation 6.3-7. You can find relationships for all these. So for instance, if a problem statement mentions percentage saturation, you'd know to come to this section of the textbook to look up the equation for the percentage saturation. Next, I wanted to talk about where you would go. I alluded to this in the last video, but where you would go to find the vapor pressure of water. So as I said in the last video, table B3 is the one you want to go to find the vapor pressure of water. And I said it's kind of arrayed in a weird way, so it's like a two-dimensional table. So on the x-axis down here is the first couple of digits, and then there's some additional precision on this axis. I think I said x-axis here, I meant y-axis. So let's say, for example, that your vapor pressure, you wanted to know what the vapor pressure of water is at 10.5 degrees Celsius. I would go to 10 over here and then over a couple columns to the 0.5 to find 10.5 degrees Celsius. And this would be my vapor pressure in millimeters of mercury. And there's 2 pages on this table. So last time, remember, we had to find the vapor pressure at 52 degrees. So I'll show you exactly where I found that number. 50 degrees C, and then 52 is where I found the vapor pressure at 102.09 millimeters of mercury. So once again, it's a bit of a weird way to array the table, but it makes sense once you know what you're looking for. The other table that you could go, so table B3 is just for water. For all other chemicals, you want to go to table B4, and this is where you're going to find the Antoine's constants. Listed in alphabetical order, values of A, B, and C, and like I said, the table has the form of the Antoine's equation. So in general, different resources may list a different form of the Antoine equation for different units. You want to pay attention to its log instead of ln, even though you can have an Antoine's equation in terms of ln. And it is for P star in millimeters of mercury and temperature in degrees Celsius. So keep all those things in mind. So let's get to a quick practice problem. This practice problem is 6.8 in your book. It says liquid methylethyl ketone, or MEK, is introduced into a vessel containing air. The system temperature is increased to 55 C, and the vessel contents reach equilibrium with some methylethyl ketone remaining in the liquid state. The equilibrium pressure is 1200 millimeters of mercury. So part A says use Gibbs phase rule to determine how many degrees of freedom exist for the system at equilibrium and state the meaning of the result. So I'm going to draw a picture. Let's say I've got a vessel here. I've got some liquid methylethyl ketone remaining, and I've got some vapor as well. So in my vapor phase, I have air and MEK both. In my liquid phase, I just have MEK. So this is, again, an example of a single condensable species, which is methylethyl ketone. Air cannot condense. So by Gibbs phase rule, I have 2 plus 2 minus 2. The 2 are for components, air and methylethyl ketone. This 2 is for phases, liquid and vapor. Once again, components are air and methylethyl ketone. Even though air is not condensable, it still counts as a component, by the way. Phases is vapor and liquid. Equals 2. So that means I need 2 variables out of temperature, pressure, and the vapor phase mole fraction. I have temperature and I have pressure. So since I have 2 variables that I need to specify, but T and P are set or specified, system is satisfied, or Gibbs phase rule, Gibbs phase rule is satisfied, rather, is satisfied. So I get students that ask the question sometimes of like they get confused because I said Gibbs phase rule is like a degree of freedom analysis, but before when we did degrees of freedom analysis, we always wanted the answer to be 0 because that tells us that our system is specified. For Gibbs phase rule, you can kind of do the same thing where you just do the degrees of freedom and then after that subtract the number of intensive variables that you have set already. So by doing Gibbs phase rule, I would get a result of 2. I would then subtract 2 for P and T to get 0. That would be how I'd think about it. I'm not sure why, I mean, Gibbs phase rule is often not really thought about in that way, but that helps me to keep it straight in my own head. So this means that I can find what the mole fraction of methyl ethyl ketone is. Okay, so part B says mixtures of methyl ethyl ketone, vapor, and air that contain between 1.8 mole percent and 11.5 mole percent can ignite and burn explosively. Determine whether or not the given vessel constitutes an explosion hazard. So in order to determine what the mole fraction is and whether or not it falls in between these, the lower limit and the upper limit, we have to calculate what it is. So let's calculate Y methyl ethyl ketone times total pressure is equal to P star of methyl ethyl ketone at 55C. So I also want to make a quick note that when I write parentheses here, this does not mean multiplication. Does not mean multiply. But the only reason why I write parentheses T is to remind myself that vapor pressure is a function of temperature. So sometimes it can be a little bit confusing of where T comes into this expression. And it does me good for keeping it organized to remind myself that temperature is within this P star equation. All right, so in this equation, I have that P is 1200 mmHg, but I don't know what P star is. So in order to figure out what the mole fraction is, I need to figure out what P star is. Similar to my water problem from last time. So I'm going to need to use Antoine's equation. So I know that P star by Antoine's equation is going to be 10 to the power of A minus B over T plus C. And T in this case is 55C. So I need to go to table B4 and look up what the values of the Antoine's constants A, B, and C are. Okay, I'm back in my textbook. I'm going to scroll down in table B4 till I get to methyl ethyl ketone. And quickly, I like to double check and make sure that my temperature that I have, 55 degrees, is within the range. So there's no need to worry there that my temperatures is within the range and I can safely use these numbers. So I've got an A value of 7.06356. I don't know why they give you so many significant digits here. I generally round, but you can keep them if you want. That's fine. These are all experimentally determined values, so you can assume that they're reasonably accurate. So I'm just going to copy these from the textbook into my OneNote. Okay, back in OneNote, I've just transcribed my values for A, B, and C, meaning that this problem now becomes simply plug it into my calculator. So on my right-hand side, I've got 10 to the power of A minus B over T plus C. I now know what A, B, T, and C all are. So my right-hand side of the equation, I get it working out to 323 mmHg. And if I solve for Y, MEK, I get 323 divided by 1200. And that answer is 0.27. 0.2, well, technically, yeah, the three significant digits, it's 269. So this is equaling 27% MEK. So let me go back to the problem statement and see what exactly it wanted me to find. Mixtures of MEK vapor and air that contain between 1.8 and 11.5 can ignite and burn explosively. So because I have 27 mole percent MEK, I don't have a danger here. This particular explosion is not susceptible to igniting. Now, a way I can turn this question around, interestingly, is I could ask at what temperature do I have a problem? So 55C is really warm. What happens if I cool this down? If I cool it down, you can imagine some of this MEK that's in the vapor phase is going to condense. So I could now ask a question, at what temperature T does it become dangerous? And here I'm just flipping around what is known versus what is unknown. So my Y-methyl ethyl ketone is going to become dangerous when Y is equal to 0.115. So 0.115, and I'm assuming that the pressure is the same, 1200 mmHg. The problem should state that. It should say at what temperature, assuming pressure stays constant, does it become dangerous, is equal to P star, and this time T is the unknown of MEK, and that is 10 to the power of 7.06356 minus 1261.339 divided by T plus 221.969. So this equation looks a little bit trickier to solve, but still doable. Right, I can still do that without much issues. Here's an intermediate step of algebra. So I just took the the log of both sides to get rid of this 10 to the power of. I can compute the left-hand side and then simply solve for T. So I'd add this term to both sides, subtract this log term from both sides. So here's some more intermediate math, and finally the last step will be solving for T, which is 34.2 degrees C. So if the temperature drops to this value while the pressure stays constant, I'm going to have a potentially dangerous mixture of methyl ethyl ketone. Okay, and that's all that I had to share for single condensable components. In the rest of the class for today, I'm going to share some Excel tutorials. So we're going to start using Excel a little bit more in this class. And I have some videos that are useful to get you started with Excel. Particularly, I have one about using GoalSeek. So if you're unfamiliar with that particular tool in Excel, I think you'll find that it'll be a very useful thing that you can use starting in this class and definitely moving forward in the rest of your curriculum. So that's all for class today after those other two Excel videos, and I'll see you in the next video.